Hi everybody, hi, Mike here. Today we're going to sort of shift directions. We're going to talk about not just individual atoms, but how they start bonding with each other, particularly covalent or molecular bonding. And before we do that, we've got to talk about the difference between valence electrons and core electrons. And our whole goal is to be able to draw structures of molecules depicting which atom is bonded to which. So what I'm going to do here is I'm going to go ahead and take the electron configuration of sodium, 11 electrons. Here's the electron configuration of sodium, right? As you folks know, 1s2, 2s2, 2p6, 3s1. Now, you will notice that in a filled shell, which is what's important because the Octet Rule, those are called core electrons. And because they obey the Octet Rule, nature's pretty happy about them just staying there. The outermost shell that is unfilled, if there is one, is called the valence shell, and these are valence electrons. So we would say that sodium has 1 valence electron and 10 core electrons. Let's move down a little further. So let's go to aluminum. All right. Aluminum has 13 electrons. Notice the number of core electrons would be the same as that with sodium. 1s2, 2s2, 2p6, 3s2, 3p1. So aluminum, or as they say over in Australia, aluminium. I don't understand that. Like when they eat something that tastes good, do they go yum, yum? Anyhow, these would be core electrons, 10, but 3 valence electrons. So we're going to end up talking about everything, not in reference to core electrons, but all the action is in the valence shell with valence electrons. So how many valence electrons does every single atom that we're going to talk about have? Well, let me show you. Check this out. Your buddy Mike is old enough to remember the days when the periodic table was always numbered in 2 groups. We would call this section the main group and the outer fringes the main group, and we'd call this the transition metals, and we still do that, but we would number them differently. We'd call these groups 1 through 10b. Now here's where we're going to focus. We're going to focus on non-metals. So let me zoom in here and show you this, all right? You're not going to see this as much anymore. But what they would do is they would number the periodic table the way it is now, 1 through 18, which just makes parts of my anatomy tighten up because it makes it seem like every single part of the periodic table is the same and just slap a number 1 through 18 on it. But you'll notice if you number it the old way, where the main group is numbered 1 through 8, the group number is simply the number of valence electrons. So there's, the alkali metals, which we were just kind of talking about. Whoops, hey, focus. Sodium in group 1A has 1 valence electron, and magnesium has 2 valence electrons. We were talking about aluminum is in group 3A. So if you just number the periodic table 1 through 8, you're going to find the exact number of valence electrons. So let's not worry about here. Transition metals, that's all chaos going on in there. So 1 valence electrons, 2 valence electrons for the whole family. Skip these guys. 3 valence electrons, 4 valence electrons, 5, 6, 7, 8. Interesting, 8. Kind of sounds like 8 in octet. So we're going to have to write the octet rule over again, except in terms of valence electrons. Let's do that right now. There, folks, is a restatement of the octet rule in terms of valence electrons. And that is, an atom or ion is most stable when it has a filled valence shell, and that's where the word octet comes from. In most cases, if you ignore the first period, like hydrogen, everything is striving to have 8 valence electrons. And so we can write out the electron configuration. That gives us a very deep understanding of that. But that's awful time consuming. So what we have are a new way of sort of communicating this is through a Lewis, and then that's named after a person, electron dot symbol. And that was named after Charles Electron Dot. So then what we got going on here is, if we go take the same family as sodium, we will write a dot, meaning that is its valence electron. And we go down to sodium, it's 1 dot, right? Down to potassium. Now let's say we go over a family. All right, so that's group 1, the alkali metals. Let's go over a family and we talk about, beryllium, 2 dots. And then next to sodium is magnesium. And then we go down to calcium. Notice that the periodic table repeats itself as it always does. So skip all that chaos there in the transition metals. We'll go over to group 3A, aluminum, right? And gallium. Now what happens is, just as a matter of sort of style, you keep them separated as far apart as each other. So it doesn't really, I don't really personally care where you put the dots, but that's just what you'll see. So then let's go over to, well, let me go up 1 now. This is where a lot of the action's going to be. Carbon, group 4, right? And then we go to silicon, 4. See, now you get, like in the old way of numbering the periodic table, this would be group 4A. This would be group 3. So you really don't have to do much memorizing, because it's just the group number tells you. Nitrogen, so then we got like, and then phosphorus, and you got 5 valence electrons. And then let's go, I ran out of room. Darn. Hold on. Hey there! So what I did is I took all the non-metals, that's where we're going next, guys, and I wrote there a Lewis electron dot symbol, and then that can be used to explain a whole bunch of stuff. For example, why are all the noble gases stable? It's because they got 8 valence electrons. The valence electron is filled. So let's talk about ionic bonding one more time. By the way, so group 4, 4 valence electrons, 5, 6, 7, 8, all right? And then, you go to the next period, it starts all over again, 1 through 8. And that's where the octet rule gets its name. Let's talk about ionic bonding one more time before we go ahead to covalent world. Okay, here we go. We're going to look at ionic bonding another time. Now, here we go in terms of, hey, I almost goofed, folks. I was daydreaming and boop. Okay. Sodium from group 1 goes and meets a chlorine from group 2. And I think we've explained to you before that what's going to happen with ionic bonding is transfer of electrons, but now you can kind of see it a little bit more clearly. If after that's over with, you're going to have a sodium with no valence electrons. Now wait for it, I'll explain that. In a chlorine, actually it's a chloride, which is going to have 8 valence electrons. And what I want to say is that what's going to happen is that electron is going to go there. It's going to give a negative charge to the chloride. The sodium is going to be positive 1. And now what I want you to kind of realize is that 0 valence electrons is really kind of just as stable as 8, because below that shell where the last electron went away is another filled shell with 8 valence electrons. So none for metals is just as stable as 8. And now what happens is these two are inseparable from each other. It's like an electron love fest, all right, where they're attracted to each other because now they have opposite charges and they're stable. So that's how ionic bonding works. Okay, I'm going to tell you where we're going next and give you an example, and we'll pick it up next time after one more thing. Uh-oh, what happens here now? Chlorine runs into other chlorine. Well, this is going to be a sea change of thinking, folks. And I think I've alluded to the fact that half-filled orbitals, they can overlap. And so what happens is they will share. Seems like it's cheating. You know, if this was the shadow banking industry, it would make sense. But this is, where'd the 2 electrons go? Did it go to one atom or the other? Yes. It's owned by both atoms. And so that's the way that the octet rule can be obeyed with non-metal versus non-metal. So we have some nomenclature here. These are called bonding electrons, and these are called, you can call them a couple, bonding electrons, and these are called a couple things. You can call them non-bonding electrons, and a kind of cute slang for it is lone pair. Now back to the electron configuration. Remember when we had filled p orbitals? That's what was up here, right? So you go and you look at the electron configuration of chlorine, and it's 3s2 3p5, and then one of the dashes would be filled up, and then the other one in 1/2 filled. And so that's really the shorthand notation that we led up to, but we couldn't tell you about it until we did electron configurations, and so that your knowledge is much richer now. So next time what we're going to talk about is what happens when you don't have just 2 atoms. What happens when there's like 5? What's going to happen is something different. I'm trying to be mysterious about it. Hey, hold on, I got to show you something. I found a robin egg. I found a robin egg in the backyard, and I knew, it was like 30-some degrees out, and so I dissolved the shell off of it in vinegar. And it looks like it doesn't have an embryo in there, so I feel good about that. And I could have fried it up, I guess, in retrospect, but that's vinegar dissolves calcium carbonate, as you folks know, because we talked about that before. Okay, I just wanted to show you that because I'm pretty proud. Okay, see you next time. Bye.